In this video, we're going to demonstrate the method of subdivision can, for regular polygons at least, be shortened to just the Apothem equation, which is given as an SA over 2 is equal to the area of the polygon in question, where n is the number of sides of the polygon, s is the side length, so really this is the perimeter, times the apothem over 2. Okay, so in the text we were discussing about how you find a by using subdivision you can take a hexagon, break it down into several equilateral triangles. We're actually going to do that at this point. So we start off with a line and its segment AB, which is one side of the hexagon. Okay. We create the center of the circle, okay, knowing full well that the hexagon is made up of equilateral triangles. Basically, we start by creating an equilateral triangle. Okay. So we know that this is the center of a circle because all the other sides are going to be just as far away from this point. Okay. So we're going to create a circle from here all the way about that runs through both points A and B. All right. So we now have a circle where we're going to draw that inscribed polygon. Okay. All we really need to do, though, is just note that A is the same distance away from our next polygon side. That intersection is the same distance away to our next one, is the same distance away to the one after that, and so on and so forth. Okay, all the way around the circle, and our last one should be the same distance away to B, which is a little wider than I was expecting, but not bad. Okay. So we have that, and we're just going to create our hexagon. This is a regular figure because all the side lengths are the same, even though the construction was a little off. Okay. You would just repeat that until you got the correct one if you were terribly interested in making it perfect. Okay. And then we have the other one, which is clearly ever so slightly shorter than the others. Okay. So we have what is a regular hexagon here, or close to, similar enough. Okay. And if you recall, what we were doing before was subdividing it into equilateral triangles, which of course we would just make by connecting all of these figures. Okay. Now, the apothem is just the shortest distance from an edge to the center. Okay. Well, clearly for an equilateral triangle, that's just the perpendicular bisector. So we again make that distance. Okay. Sweeping out our two circles. Okay. And drawing that line. Okay. So that is a right angle. This is a apothem. This is the apothem up here. Okay, that entire line. We also know that since this was a 30-60, or I'm sorry, a equilateral triangle, that it breaks it down into a 30-60-90 triangle, which we determined what the relationships were for much earlier in a prior chapter. Okay, so what we really have here then is a way of determining, okay, what is the total area? Before, we showed that the area, just by finding all of these equilateral triangles and adding them all together, was equal to the side length A squared times 3 root 3 over 2. Okay? We're going to show that that's the same thing for here. Okay? With a side length A, okay, we apply our formula, okay, such that we have, by the Apothem method, we have 6 sides of side length A times the apothem, which unfortunately is also listed as A here. What is the apothem, though? Okay, so I'll write it as AP. The apothem from our 30, 60, 90 triangle relationships is really just going to be A over 2 root 3. Okay, so this is A over 2 root 3. Okay, all divided by 2. What is this overall? Well, this is equal to 6a squared root 3 over 4, which is the same as saying 3a squared root 3 over 2, which is identical to when we were doing it just by using the area of all the internal equilateral triangles. The good thing about this is that you don't need to subdivide completely. So this is actually a shortcut should you happen to know what the apothem is for a given regular polygon. Again, regular just means that all the sides are of the same length and all the angles are the same.